I'm Anil Kumar sharing with you a concept about understanding second derivative. The main question here is, what does second derivative say about the graph of a function? Is it concavity? Is it maximum? Is it minimum? Or what? That is what we are going to discuss in this particular video, right? Now I'm going to use few terms. Let me define all of them first. First of them, of course, will represent function as f of x, and then we'll have the derivative of the function. We'll call this as the first derivative. And then the second derivative. To understand it better, let me sketch a graph here so that it makes some sense. With graph, it is easy to explain. So rather, I'll sketch two different graphs. Let us say that we have to go from point A to B. So here is point A, and we want to go from here to there. And the path taken is kind of like this in one case. In the other case, let's say from point A to B, we go like this. Now, both ways, we reach from point A to B. However, as far as the function is concerned, there is a very different shape, right? So for the function f of x, in the first case, let us say, you will notice that if I draw tangent lines to the curve, now these tangent lines basically represents derivative, right? So these tangent lines represent derivative. So we'll say f dash x, right? What do you notice about these tangent lines? Okay, let me make tangent lines in the second case also to points on the curve, right? So see these three, right? So these are my tangent lines. Tangents, the slope of the tangent is the first derivative. Now what you notice here is that in the first case, you notice that graph is above the tangent, right? So here we notice that graph is above tangent. And in the second case, graph is under, or you can say below, tangent line. So that is one huge difference between the two. What else do you notice? Well, all along this path, what we notice is that the slope of the tangent increases, right? So in this case, we notice that it is kind of zero. It goes positive and higher positive, right? So all along the path from A to B, slope, or you can say f dash x, increases. And in the second case, what you notice is that the slope or the derivative, f dash x is the derivative, right? Decreases. So here from high to almost zero, here from zero to high. So it is kind of increasing all the way. Here the slope is decreasing all the way. Now, if that is the scenario, what do you think will be the value of the second derivative? How will the second derivative be? Now, second derivative is rate of change of the first derivative, correct? So we know that second derivative is rate of change of f dash x. Now here it is increasing means the second derivative all along this path is greater than 0. And in the second case, the second derivative should be less than 0, right? So we have done no calculations, but that is what we can infer from the simple sketch we have made. Perfect. So in case 1, second derivative is greater than, it is increasing greater than 0. In the second, since the slope is decreasing, rate of change is also decreasing. Perfect. Now that's a huge thing. Now from here, we can say about the graph. If we go backwards, right, let's go backwards. Now we say if second derivative is greater than 0 on an interval, let's call this an interval, on an interval. In that case, slope of the function increases and the graph is above the tangent line. You see that part? So if the second derivative is positive on an interval, in that case, slope of the function, that means first derivative, increases and the graph is always above the tangent line. And if the second derivative is less than 0 on an interval, in that case, what happens? The first derivative is decreasing and the graph is under the tangent line sketch. Perfect. Now, this is such a useful concept. And from here, we'll also say one thing, shape of the graph. This shape is called concave up. So the graph which we have drawn in the first case, we'll call this as concave up. And in the second case, it is concave down. Concave down. So now, we are what are we considering? We are considering f of x a continuous function. Right? So we can from here say that if the second derivative is greater than 0, in that case, over interval I, so I is the interval, over the interval I, if the second derivative is greater than 0 over the interval I, f of x is concave up. And if the second derivative is less than 0 over interval I, then the function is down, concave down, I have to write, okay. Does make sense to you, right? So that is what we could conclude from this particular situation. So what we can say that the second derivative defines the graph of a function. So it could be concave up or concave down in a given interval if the second derivative is always increasing or always decreasing, as shown here, right? Now let's look into the second part, which is when will it be maximum or minimum? Perfect. Now getting back to our question, what does second derivative say about the graph of a function? We learn definitely one thing, and that is if the second derivative is greater than 0 over an interval of a continuous function, then the graph is concave up. We also saw that in this case, if the first derivative is this, in that case, this is first we could infer. Second, we learned that the graph will be above tangents to the curve. Very important criteria. In third, you will also notice that the first derivative is increasing. That is why the second derivative is greater than 0. Perfect. Now in the second case, if the second derivative is less than 0, in that case, what happens? You can write it down. Perfect. And in all the three cases, we are talking about continuous function, rather interval. We'll call this interval as I, right? Continuous interval I. So all this is being defined in a continuous interval I, correct? So what happens when the second derivative is less than 0? In that case, it is concave down, graph below tangent line, and f dash x is decreasing. Perfect. Now, let us see a graph which is kind of like this, that is, which has combination of both, right? So, which normally a graph could be, right? So, something like this. Now, in this case, let's try to analyze the concavity, maximum, minimum, and the effect of second derivative. Let us extend our knowledge and apply it to a more complex graph. So, let me sketch one here. Let us say that it's a graph of a continuous function, which is kind of like this, right? So, now in this particular case, what do you notice? You notice that there is a portion which is concave down. So, we can say from here to here, the portion is concave down, right? In this portion, if I draw any tangent line, then the graph is below the tangent line. Do you see that? On the other hand, we have a portion where it is concave up. Now, in this portion, if I draw a tangent line, the graph is above. I'm purposely keeping the lines away. You can clearly see that graph is above the tangent line. Correct? Now, in between, we saw that the tangent line slope, when it is concave down, is actually decreasing, right? So in the first portion, let's call this as concave down portion. In this portion, we notice that the function, which is second derivative, is always, because the slope is decreasing, right? It's going from positive to 0 to negative, is less than 0. Now, in this portion, when it is concave down, we also see one maximum point. So it goes over a hill. So you notice a maximum point here. Now, how do we verify that this is indeed the maximum point? That is a huge question. So in this part of the curve, you notice two things. That is, at maximum, the derivative of the function is going to be 0. Right? So for a continuous function, derivative is 0, second derivative is less than 0, and this combination gives you maximum. Perfect. Now let's look into the other part of the graph, which is concave up. Now in this part of the graph, since the tangent slope is going from negative 0 to positive, we know that the second derivative is greater than 0. But somewhere in between, let's call this as a point B, we have a minimum value. Slope of tangent is 0, right? So at this point, the derivative of the function is 0. That is also a critical point. So this combination gives you minimum. Normally we call them local maximum and local minimum. We're only looking into a part of the function, right? So local maximum and local minimum. So that is what is another thing which you get from the second derivative. We actually call it a second derivative test. So second derivative test, let me write down here. Confirms if we have local max or min at a critical number, right? Now, what is a critical number? Let me write down that also. So I'll write in different ink, critical number. Critical number is a point where the derivative is either equal to 0 or the derivative, only the derivative is undefined. Is it okay? So we could get a critical number at one of these points. So in this particular case, we concluded that the first derivative is 0. Right, so it's a critical number, horizontal tangent line, perfect, in this particular case. And we also saw that the second derivative is equal to 0. Now when that happens, you get a local maximum or a local minimum. Is that clear to you, right? Now taking into consideration about the undefined, we could have another example, right? So which we'll do in another video. We could have a function which could be kind of like this. So I'm just drawing a function here, kind of like this, right? So we do have a minimum here, right? So at this point, what we notice is the derivative of the function is undefined. At this point, let's call this point P, right? At P, right? Cusp for a corner, the derivative is undefined, and we do have a local minimum here. Perfect. So that is another example which we will be doing in details in later videos. But however, I hope this point is clear that when the first derivative is 0 and second derivative is less than 0, in that case we have a local maximum. And when the first derivative is 0 and the second derivative is greater than 0, then it's like concave up, you have a local minimum. Perfect. And now let's talk about this point where the concavity changes. Now let's look into the third very important part of our learning from second derivative, which we call point of inflection. Now point of inflection is a point where concavity changes. Right, so it could change from, let's have a scenario kind of like this. Let me just make like this. So we have a curve of a polynomial where you will notice that up to this point it is concave down, right? So this portion is concave down. Let's call this point as A, and from here to, let's say, the point B, it is up. Now if the concavity changes from, let's say, concave down to concave up, In that case, we have a point of inflection. Now we know that in this part where it is concave down, the second derivative is actually less than 0, and in this part the second derivative is greater than 0. So that means, what is the value of second derivative at A? In between these two, we are left with only one value, which is 0. So at point of inflection, the second derivative is equal to 0. Right? So we have two scenarios here for point of inflection. So what we could say is that if, let me put it the other way, if the second derivative is equal to 0 and concavity changes, on either side, then there exists a point of inflection. So it could change from concave down to concave up, or also the other way. It could also be from concave up to concave down, as you can see here, right? So it is now concave up and then again down. So at this point also, what we know is that the second derivative is 0, concavity is changing. Perfect. Since the concavity is changing on either side of a point, we call this as a point of inflection. Correct? So that point represents a point of inflection, and at this point the derivative, the second derivative, should be 0. Now there could be situations where we may have second derivative as 0, but since the concavity may not change, we may not have point of inflection, right? So that is also very important to understand. For example, we could have a situation like this. Now here, both sides it is concave down. So this point is not point of inflection. Is that clear to you, right? So concavity has to change and second derivative has to be 0 for a point of inflection to exist. Right. So I hope that point is absolutely clear. So let us summarize our learnings about the second derivative. We notice that the portion of the graph which is concave down, here the tangent is always above the curve. And if we have concave up, in that interval, tangent will be below the curve. A maximum can exist on concave down portion and a minimum could exist on the concave up. That is to say, in the interval where the second derivative is less than 0, we could have a maximum provided the first derivative is 0. So that condition gives us local maximum. First derivative being 0 means we have a horizontal tangent line. And if this horizontal tangent line exists on concave up portion, in that case we have a local minimum. We also saw that change of concavity leads to a point which is called point of inflection. And if the concavity changes from concave up to down or from down to up, then in between we have the second derivative which is going to be 0. At this point there exists a point of inflection. With that we'll conclude, and I hope you find it interesting and useful. Feel free to write your comments and share your views. If you like and subscribe to my videos, that would be great. Thanks for watching and all the best.